missing the letter. All right. So today we're going to transition from the nice convergent sequences that we were talking about to something which is exactly the same, namely convergent series. Ah, yes. Yeah. Today we're going to get series. Okay, and the discussion of series, which will last for much longer than today, will be interrupted in the middle by something that it's going to require for later on, which is going to be improper integrals. So get out your Emily Post. Nobody knows who that is, do they? Not a clue. Viewers, what am I going to do? Emily Post. Huh? No, yeah. Emily Post, the inventor of the Post-it. No. Oh, dear. I'm going to go nuts. What's that? What is Emily Post? Or who is Emily Post? Emily Post is one of the foremost experts on manners and etiquette. And she's written, several books on it. And so we have improper integrals. It was funny to me. Okay, so let's recall a few things. This is it's like when you turn on one of your favorite TV shows and they have the recap, what's happened the last 6 episodes. All right, so recall that last week talked about sequences like this. And if you started with a sequence, then there were 2 very interesting things that we could talk about. One was convergence. Right? We talk about a sequence converging to some limit L. And recall that this meant that, well, the terms of the sequence should get close and stay close to this L. Right? How close? Arbitrarily close. Right? And what did arbitrarily close mean? That meant that, okay, as close as you want to get for any small number epsilon, you can go out far enough. Okay, so this n, you probably were discussing with Edgar, is dependent on how far you want to, on how close you want to get. Right? So if you want to get this close, you can go out far enough such that an and L are within epsilon of each other for all n past this big N. Okay, so that's what it meant for a sequence to converge. If you went out far enough, it got within epsilon of this limit L. Okay. Another thing that you could do with a sequence is you could automatically build another sequence. Actually, there's a lot of sequences you could build. One of them was the absolute value sequence, where you just took the absolute value of each term. And we had a really nice theorem about that. It said that if the absolute value sequence converges to 0, then the original sequence converges to 0. But another sequence you can get, and this was the very first one we wrote down, was called the sum sequence, or the partial sum sequence. Okay, so an gives an plus. And remember, in an plus, well, the first term is exactly the same. And after that, it starts to look like so, right? If you want to get a2 plus, you just add up all of the terms up to a2. Right? a3 plus was a1 plus a2 plus a3. Right? And an plus is a1 plus a2 plus an. Okay, so you get a new sequence. This an plus. And well, we just saw it. With any sequence, you can ask if it converges. Right? And so we want to ask, if I start with a sequence an, well, I can ask if that converges. But I can also take the sum sequence and ask if that converges. Now, earlier we said, if you want to take all of the terms in the sequence and add them up. Right? Well, formally, this doesn't, you can write this down, but it doesn't make any sense. I mean, how can you add up an infinite number of things, right? Our operation isn't defined that way. Okay. So we put quotes around it. So maybe we'll use the following symbol, A, whoops, around, A infinity plus. Okay, I just use this symbol here. Okay, what should this mean? Well, this just means you add up all the terms in the sequence. All right? But we'll put quotes around it. Right. And you don't stop anywhere. Just I've shown AN, but you just keep going. Okay? You just can write this down, right, as if it had some meaning. Okay? But right, in the beginning, it has no meaning. Right? You can't add an infinite number of things together. We don't know what that means. Right, well, now we want to give it a meaning. Okay, by the way, we're also going to write this in the following way. Okay, again, here I'm doing the sum n equals 1 to infinity of an, right? This just means a1 plus a2 plus a3, and you don't stop. You keep letting n go as big as it could get, and you take all the terms at once. And again, this, again, has no meaning. Right? We have to assign it a meaning. Well, we're not always going to assign it a meaning. We're only going to assign it a meaning in special cases. Namely, and by the way, these are what we call a series. Right? Remember, this is how we defined it on the first day. The way we're going to assign this meaning is we're going to look at the sum sequence, an plus, and we're going to ask if it converges. If that sequence converges, then we're going to let whatever that limit is, whatever the L is, that's what this sum is going to equal. Okay, you're going to take the limit of all of these partial sums, right? They get bigger and bigger and bigger. And if that converges, that's what we define to be the sum of the infinite sum. Okay? So if an plus converges to a limit L, then we define, this is a definition, the sum n equals 1 to infinity an equal to L. This is a definition. And we call this a convergent series. Okay, it's always a series. You can formally write this symbol down, right? And this is what your series is. That's your series. But if this partial sum sequence, this sum sequence converges to L, then we call the series a convergent series. And what do you think we call it if it doesn't converge? Yeah, a divergent series. Otherwise, it is a divergent series. So as a first example, we take 1 plus 2 plus 3 plus on forever. Okay, this can be written as the sum n equals 1 to infinity n. Okay, the nth term in the sequence is n. Okay, so this is a series. Does this series converge or diverge? Well, let's see. Let's look at the partial sums. Okay, we're going to look at the sum sequence. Right? The sum sequence looks like 1, 3, 6. Right? I'm adding 1, 1 plus 2, 1 plus 2 plus 3, 10. Is this going to converge to some number? No, right? This goes to infinity. Okay, so this says that the sum n equals 1 to infinity of n. Right? This diverges. Right? Okay, it's a divergent series. Okay. So, but we're not really doing anything new here. Right? in the end, all we're doing is talking about a sequence and whether it converges. A convergent series is really just a convergent sequence. There's nothing new. It's just new words. What's the difference? A series is always coming from a sequence. All right, you start with a sequence, you build a series. But the series is really just talking about the limit of your sum sequence. All right, you start with a sequence, you build a new sequence called the sum sequence, and the series exists, that is, it converges if this sum sequence converges. All right? So when you start with a sequence, you have two questions you can ask immediately. Does the sequence converge, and does the sum sequence converge? Yes. All right. Well, the series is what happens when you take the last term in the sum sequence. Okay, that is, you take all the terms and add them together. Yeah. Okay, so this one is bad. Okay, so let's see one that's good, right? One that's going to converge. So this is one that you've seen before in your lives, I'm sure. And this is called a geometric series. So for a geometric series, we're going to start by letting A be a real number and R, little r, a real number. Okay, so let me first consider a sequence. The sequence is going to look like A, that's going to be the first term. And then each term in the sequence after this, I'm just going to multiply by r. So for here, I'll go from A to AR. Okay, multiply by r. Now I'm going to multiply by r again. And I get AR squared. Yeah? Yes. Yes. So, well, formally, the series is this thing in quotes. Right? It's just... Yes, but you don't even have to, and you don't even think about it as the actual answer. Exactly, as the expression, the formal expression. That's the series. Right? And then we can say a series converges to a number. Right? And the reason why we have to say that is you can't add an infinite number of things up. It doesn't make any sense. Right? Our operation of addition isn't defined that way. You can always have a series. You can always write it down. You just can't evaluate it using plus, really using plus, unless it's finite. Okay, so let's get back here. Right, so we have each of these terms, and we're just going to keep multiplying by r. You get AR cubed, AR to the fourth, and so on. Okay, so that's our sequence. And now we build the sum sequence. Okay. So the sum sequence is going to look like A plus AR, A plus AR plus AR squared, okay, and so on. Okay, so that's your sequence. And that's the sum sequence, or partial sum sequence. So let me say, I use A normally for my sequence letters, but since I already have an A in here, let me call this sequence Sn. Right, so the nth term. Right, well, let's see what the nth term is going to be. And this, by the way, would then be Sn plus. Okay, so what here would be the nth term? Well, let's see. When n is 1, you get an A. When n is 2, you get AR to the 1. When n is 3, you get AR to the 2. So it's going to be AR to the n minus 1. That's the nth term in the sequence. Yeah? Right? The fifth term in the sequence, 1, 2, 3, 4, 5 AR to the fourth, right? 5 minus 1. Okay, and then Sn plus, right? That's A plus AR plus AR to the n minus 1. Okay, now before we talk about the convergence of this series, let's see, where have you seen this series before, right? Well, it's actually been the example that we've used, well, it's at least in a dead heat for the most one we've used, right? We've used this quite a bit as an example. What's the other example we've used? It wasn't 1 over n squared. You got them, the n and the square mixed up. There was 1, and then, actually, we threw out the 1 even, but we started with a half, and then a fourth, and an eighth, and a 16th. Right, so 1 over 2 to the n. Right, so an example of such a sequence would be, I'll start with a equal to 1, and r equal to a half. So your sequence would look like 1, okay, then you multiply by a half, then you multiply by a half, then you multiply by a half, you multiply by a half, and so on. Yeah? Is it true that it's always going to have a limit? No, because, well, for instance, it could diverge. Well, here, for instance, right, this was a series, right, and you could view it as a sum sequence. Okay, the end of the sum sequence, right, is when you add them all up. Okay, and what would be the limit of this sequence? 1, 3, 6, 10, 15. Right? It doesn't have. I mean, it goes to infinity, right? There's not a real number limit. Right? So remember, in a sum sequence, you keep adding things. If the things you add are getting bigger, this is really bad, right? If they're adding 10 and 100 and 1,000, I mean, there's no way this is going to converge to anything. Right? Now, if they get smaller, then you have a chance. Right? Not guaranteed, and we'll see an example later where it doesn't work, even though they're always getting smaller. Right? But here it will work, right? And here you have a chance. So here, incidentally, right, this would be a nice geometric. Well, this would be this is the sequence, okay, and then the series that you get from it. Right? Well, first you start with the sum sequence, which is going to be 1, and then 1 plus a half, right? 1 plus a half plus a fourth, 1 plus a half plus a fourth, whoops, plus an eighth, and so on. By the way, we can compute these. This is 1. This is 3 halves. This is, what is this going to be? 3 halves plus another fourth. 7 fourths. Okay. Next one. Not 15 fifths, but 15. Notice the denominator and the last term. 2, 4, 8. You can put all these over 8. That's why it works that way. And notice the difference between the number you're getting here and the number 2. Okay? This is missing 1 from being a 2. This is missing a half from being a 2. This is missing a fourth from being a 2. This is missing an eighth from being a 2. Right? So in fact, you can actually get the sum, or the term in the sum sequence, just by saying 2 minus the last term in the sequence. And I'll actually do it. Okay, so what do you think this thing is getting very close to? The 2, right? It's always missing it by this last term in the sequence. And that last term in the sequence is getting arbitrarily small, so it must be getting arbitrarily close to 2, so it's probably converging to 2. Okay? Okay, so this, if you take the whole thing together, right, then you get the series that corresponds to it. And the series, right, is 1 plus a half plus a fourth plus an eighth, and we put this in quotes, plus a 16th, right, plus dot, 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 and it's the whole thing. Okay? And what we would like to show is that our intuition is correct and that, right, this sequence converges to 2. Okay, so this would be a convergent series. Even though it makes no sense to actually add up all these things. You can't add up an infinite number of things. We can define the sum of these infinite things, right, formally to be 2, because the sum sequence converges to 2. Okay, so let's see if we can prove it. Well, let's look at a couple special cases about this geometric series. First, what if R is greater than or equal to 1? What's going to happen when I multiply by something? Well, first, how about R equals 1? I mean, that's maybe the easiest case. Say R equals 1. Right? What does our sum sequence, our series rather, look like? Right? That's our series. Because I did all of them. Right? What does it look like when R is equal to 1? Well, if R is equal to 1, then it's just n equals 1 to infinity a. And, well, as long as, if a is 0, this is not such a bad thing, right? It would be 0 plus 0 plus 0, and it makes sense that's going to converge to 0. But if a is anything other than 0, what's going to happen to this? Yeah, what's going to happen? Well, what is the sequence? What's the sum sequence which is corresponding to this? Right? The sum sequence is what? Well, the sum sequence, right? You're not going all the way to infinity. You just add one more term each time. Okay? The sum sequence becomes a, right, and then a plus a, which is 2a, 3a, 4a, so forth. So it equals, well, n times a. Right? N goes from 1 to infinity. So if a is non-zero, does this sequence, what happens to the sequence? Goes to infinity, right? Because n is going up to infinity, and a is just some fixed number. Multiply any number other than 0 by numbers which get bigger and bigger and bigger, it's just going to keep getting bigger. So this goes to infinity. So if r is equal to 1, that's what happens. Okay, that's very easy to see. Now, what about r greater than 1? Well, if r is greater than 1, then each of these r's to a higher power, right, those are going to get bigger. So it's actually going to get worse. Right? Instead of just having a couple of copies of a, in the next term you're going to have a plus something bigger than a. Right? And then a plus something bigger than a, then something bigger than that. So it's also, right, that's also going to diverge to infinity. Okay, so those are already bad. Okay, so our only hope is if we can make our terms smaller each time. Right? So how can we make our terms smaller? Right? Let's let r be less than 1. Now, we don't want to make it too small. So let's start by squeezing it between 0 and 1. We'll worry about negative r's later. Well, if r is 0, of course, there's really no problem, right? Because then you're getting a, 0, 0, 0, 0, 0, right? If r is 0, then all these terms after a just become 0. So then the whole sequence is a, 0, 0, 0. The sum sequence is a. So the series is just a. Okay, so it's really interesting when it's between 0 and 1. So let's see what happens. So we said that the nth term in our sequence, I'm just copying from the left over here. The nth term in the sequence was a r to the n minus 1. Okay, so now I'm going to play a trick. Right? Here comes a trick. I'm going to multiply both sides by r. Why? Because it's a trick. So r times Sn is equal to what? A times ar to the n, right? Because I'm multiplying. I had r to the n minus 1, and when I put one more r, it becomes r to the n. There's n r's instead of n minus 1. Okay. Now, what good does that do me? Well, let me subtract one from the other. So let's see, Sn minus r Sn. Oh, actually, I'm messing this up. Right? Why am I messing this up? Because I don't want Sn, I actually want Sn plus. Sorry. Let's do this again here. Oh dear. This is bad. I have the wrong indexing thing here. Okay, I have to write it out. Okay. I have to write it out. Okay, so Sn plus was a plus ar plus ar to the n minus 1. And Sn, r times Sn plus is ar plus ar squared plus ar to the n. Okay, so I take this sequence, or this sum here, okay, and I multiply every term by r. So a becomes ar becomes ar squared, right? Ar to the n minus 1 becomes ar to the n. Okay, and now I'm going to subtract these two. Now, when I subtract them, something very nice is going to happen. Right? Okay, the first term, a, that's just there. Can't go anywhere. But now look at the next term, ar. And when I subtract, I'm going to subtract an ar. So they're going to cancel. Yeah? The next term in this sequence would be ar squared. But when I subtract, there's going to be an ar squared over here. They're going to cancel. Ar cubed, ar cubed. Ar to the fourth, ar to the fourth. They're just going to keep canceling. Right? Ar to the n minus 1, I'm going to subtract an ar to the n minus 1. Right? Almost everything goes away. The only thing is at the very end, I have a minus ar to the n, which doesn't get canceled by anything on the left. So I get a minus ar to the n. Okay, so now let me factor an Sn plus. And it'll give me a times 1 minus r. And on the right, let me factor out an a. And I get 1 minus r to the n. Actually, I think in the end I'll probably expand it through anyway. So let me just leave it as a minus ar to the n. And now let me solve for Sn plus. So I'll just divide by 1 minus r. Okay, so this formula is already interesting in its own right. If you don't even talk about infinite series, convergence, or anything, this is already very interesting. It says, if I want to know what the sum of the first n terms is, I don't have to manually compute the first n terms and then add them up. I can actually just take the original term and then subtract the original term times this r to the n, and then divide by 1 minus r. That's one simple calculation you can do. So for instance, that tells us that, let's say we're back on this example here, right, where a is 1 and r is a half. And we want to know the sum of the first, say, 7 terms. Okay, so over here, S7 plus, okay, well, look, I've already done 1, 2, 3, 4, 4. I've just done 4, right? The next one I have to add a 16th, and then a 32nd, and a 64th. Okay, but this formula says I can just do it outright. I can say 1 minus 1 times a half to the 7th, okay, because I'm looking for the 7th term, divided by 1 minus a half. So, and this is very easy. Okay, well, okay, I got to know what's a half to the 7th. Yeah, what's a half to the 7th? Let's see. 2, 4, 8, 16, 32, 64, 128. So I have to do 1 minus 1 over 128 divided by 1 minus a half, which is a half. Of course, dividing by half is the same thing as multiplying by 2. And subtracting 1 1/28 from 1, that's very easy. Right? It's just 127 over 128. Right? You're just missing 128, 128. Then we multiply it by 2. So that'll turn this into 127 over 64. Okay? You didn't have to add them all up. Of course, we also knew we had this other clever way, right? We just take 2 and then subtract whatever the last term should be, 1/64. Okay, but this gives us a nice formula. Okay. But we can do more with this nice formula. We can go further. Yes. Yes. So this would be 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd plus a 64th. Okay. Let me break this up into 2 fractions. So Sn plus, we said, equals a minus ar to the n over 1 minus r. But I can write this as a over 1 minus r minus ar to the n over 1 minus r. Now, let's say I wanted to add up everything, right? I want to look at the infinite series, not just the sum sequence, but I want to look at the series. I add up everything. And I want to know whether that converges. The definition, right, the sum here, okay, this exists if the sum sequence converges. So I want to look at this sequence, the sum sequence, and see if it converges. So I need to take the limit as n goes to infinity. Now this is the same as the limit as n goes to infinity of a over 1 minus r minus, I'm going to write it slightly different over here. It's the same thing, but I'll write a over 1 minus r times r to the n. Moving this r to the n out. And the reason why I do that is because the only thing in here that depends on n is this r to the n. Everything else is as far as n is concerned, everything else is a constant. Okay, now, if I view these individual terms, right, as sequences themselves, right, why would I do this? Well, I have a limit of something minus something. What do I want to do? I want to, well, if I have a limit of a difference, I want to make that the difference of the limits, right? I want to break this up. I want to be able to evaluate these separately. Okay? Now, there's only one requirement that you have to meet, namely that if you break them up, they have to converge. Okay? Then you're allowed to do it. If you have two sequences which converge, then you can break up the limit of their difference. Okay? Okay, but this sequence here, there's no n in it. So the sequence would be a over 1 minus r, a over 1 minus r, a over 1 minus r, a over 1 minus r. Of course, that converges. It's just a constant sequence. Okay, what about this one? Well, this is a constant. Okay, so it shouldn't matter. I should just be able to pull it out of the limit. The only thing that matters is r to the n. So we have to ask, does the limit of the sequence r to the r to the first, r to the second, r third, r to the fourth, r to the fifth, does that converge? And if you recall last week, that's exactly the sequence that we wrote down. And remember, we broke it down in all these cases when it was, here was a picture of the convergence. So this is for the sequence r to the n. The crucial points somehow were minus 1 and 1. Okay? It did not converge at minus 1. It converged at 1. And it converged everywhere in the middle. And it didn't converge outside. Okay. Now remember, we're in the case here where r is less than 1 and greater than 0. So r to the n does converge. Right? In fact, we knew it converged to 0, except at 1 where it went to 1. Okay. So all these things converge. So we can break up the limit. So this becomes the limit as n goes to infinity of a over 1 minus r minus, well, again, this is a constant. I can pull it outside the limit. A over 1 minus r times the limit as n goes to infinity of r to the n. Now, the first limit is silly. It's a constant sequence. It doesn't change. The limit is just what it is. A over 1 minus r. And the second one, well, since r is less than 1 here, but greater than 0, when you raise it to the n, it just gets smaller and smaller and smaller. So the limit as n goes to infinity of r to the n is 0, right? That's what we proved. Okay, so this whole bit here, this is just 0, right? So of course, if you multiply it by something, it's still 0. So this is actually the whole limit. So that's what the whole geometric series converges to. Right? So the sum sequence converges. So Sn plus converges to a over 1 minus r. And that's what the limit is. So in our case, if we wanted to add up 1 plus a half plus a fourth plus a eighth plus a 16th plus a 32nd plus a 64th and just keep going, add them all up, all we have to do is do 1 divided by 1 minus a half. And that's it. That will be what it converges to. And of course, 1 minus a half is a half. 1 divided by a half is 2. So this, the Sn infinity, right, which is 1 plus a half plus a fourth all the way, right, this equals 2. Okay, or if we put it a different way, instead of using these quotes, right, sum n equals 1 to infinity. Well, we have to write it like this: 1 over 2 to the n minus 1. This equals 2. I have to do this n minus 1 because I want the first term to be a 0. I mean a 1, 2 to the 0th power. So So this is very nice. This is a really simple formula for adding up a geometric series. Right? If you want to get the whole thing, this is really amazing. You could add up an infinite number of things, and that's the answer. It's just take the first term, divide by 1 minus the ratio of the terms. Boom, you're done. Howie. To this? To the next line? So I wanted to break up this limit. So I can't, well, what I did is I said, okay, the limit of a difference, if I have two sequences, and I take the limit of them both, I can break it up, right? But only if both sequences will converge when I break it up. Okay? So first I had to say, okay, this is a constant sequence, so it converges. Okay? This sequence converges because we know when r is less than 1, r to the n converges. That's what we proved last week. Okay? So I can break it up. So I just take the limit of the first term minus the limit of the second term. Okay, that's what I get here. And I pulled this constant out of this limit. I did that in one step, which I'm also allowed to do because I know that this limit converges. I mean, yeah, this limit exists. Okay, incidentally, if we wanted to get rid of this 1 in the beginning, right, and just add up from a half, well, it's very easy now, right? I mean, if I want to do a half plus a fourth plus an eighth and so on. Actually, I have two ways to do it. I don't know why I started using commas. One way is to note that if I add 1 to this, then I get exactly, right, this sequence. And we know what that added up to. It added up to 2. So if I get rid of the 1, it should add up to 1. Another way is to say, okay, here my a is a half, and my r is still a half. And so this thing will add up to, well, a is a half divided by 1 minus a half. That's still a half. A half divided by a half is 1. Okay. And this, by the way, is the modern answer to Zeno's paradox. If I want to walk from here to Lathe, I first have to walk halfway. Right? But before I can get to Lathe, I still have to walk halfway. Right? Before I can get to Lathe, I have to walk halfway. Right? So Zeno said, look at this. You can never get there because before you can get anywhere, you first have to walk halfway, and you always will have to walk halfway. Right? Zeno said, you have to add up all these things, a half, a fourth, an eighth, a 16th. You can't possibly do that. Right? The modern answer is no, you can. Right? It converges to 1, which is what you would expect. Okay. Okay, so we've handled half of the problem. We know that if you're 1 or bigger, then the geometric series diverges. This goes up to infinity. If you're between 0 and 1, well, at 0 it's easy, it's 0. Bigger than 0 but less than 1, it's going to converge to a over 1 minus r. Now, if you look at our argument, the only thing we used, right, about r was that r to the n converged. Right? And we happen to know that r to the n also converges between 0 and minus 1. Right? Not at minus 1, but between 0 and minus 1. So exactly the same argument will show that if r is greater than minus 1 and less than 0, right, then Sn plus still converges to a over 1 minus r. Right? There's no change in the argument. And if r is less than or equal to minus 1, then what's going to happen? Well, when you raise it to these powers, bless you, it's going to alternate between getting bigger positive and bigger negative, right? So it's just going to be these really nasty positive, negative terms that you're going to be adding on. Okay, so that sequence can't possibly, converge. Right? It's just going back and forth too much. Okay, so Sn plus will diverge. So we can put this all together in one statement. So here we have, again, A and R are real numbers. So A plus AR plus AR squared plus dot 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 equals, so this is the infinite series. It equals A over 1 minus R if the absolute value of R is less than 1. Okay, so this means it's between minus 1 and 1. And it diverges otherwise. It's actually very short statement. But this is going to be very useful. Right? When we try to actually sit down and look at different series, one of the goals is going to be to say, I can rewrite at least part of this as a geometric series. And now I can apply this result. So, one more quick example how this might show up is you might have something like this. Okay. You might have a sequence. Looks like 4, and then, or let's see, the first term, right? What would be the first term? It would be 16 over 5, and then the next one would be 64 over 25, and weird stuff, right? And you try to add it up, and, well, that's what you get. Now, I want to write this as a first term and then a ratio. I want to see somehow that I can fit this into our geometric series picture. How do I get between one term and the next in this? Right. What's the ratio of terms? Let's see. Let's just write out some terms. Okay. So if I'm just writing the sequence, the underlying sequence, not the sum sequence, but just the underlying sequence. Okay, when n is 1, I get, let me just write it like this, 4 squared over 5. The next term is 4 cubed over 5 squared. 4 to the 4th over 5 cubed. What's the difference term to term? What am I multiplying by to get from this term to this term? By 4/5, right? That's therefore your R. R stands for ratio, by the way. This A and R. Okay, A, because A is the first letter of the alphabet, and it's the first number in your sequence. R is the ratio from term to term. Right? So the R is 4/5. What's the first term? Well, we got to be careful here. Why do I have to be careful? The way I want to write this so that everything works out, I mean, I guess it's probably right, but I want to make it so it's really clear what's going on. Okay? So what I'm going to write this as, I'm going to pull one of this 4 out. Okay, there's n plus one of them. I'm going to pull one of them out. I get a 4 there, and I'm left with 4 to the n over 5 to the n. Now, let's go down here. I can rewrite this as 4 over 5 to the n. By the way, this, I just want to quickly note up here, this was equal to n equals 1 to infinity AR to the n minus 1. This was somewhat key. Okay, so I actually have an n here, but I really want to have an n minus 1 for it to match my geometric series thing. So I want to pull out another 4/5. Okay, and that'll get me an n minus 1. So I have 4 times 4/5, which is 16/5, times 4 over 5 to the n minus 1. Okay, I just took one of these 4/5 and pulled it out. And that's how I got 16/5. And now it really looks like the geometric series form. Okay, it also says that what Leith's guess was correct, right? The first term is 4 squared over 5, 16/5. Right? That's your A, that's your R. Okay, so this is right. Okay, so we can really write it out that way. Okay, and so now this is going to equal, well, 16/5 over 1 minus 4/5, which is, let's see, 1 minus 4/5 is a fifth. So that means you're just going to multiply by 5. But 16/5 times 5 is 16. Cool. So that whole thing adds up to 16. So easy. So nice. Okay. Questions at this point? Let me write down a couple of properties that are immediate from the definitions, but which we will want to use. Let's say you have a sequence, or a series rather, and another series, and that they converge. Okay, so these two things converge. And let's let C be some real number. Okay, and then we're going to get our usual sort of I can break things up properties. Okay, at least a couple of them. So the first one I'm going to write down is this. If I add the two sequences, the underlying sequences together, and then look at that series, it's going to give me the same thing as if I did them separately and added them up. Okay. And there's nothing special about plus here. Minus will work as well. And then the same thing is going to work if I pull out a constant. If I multiply my sequence by a constant, and then I look at the series, it's the same thing as if I first sum the series and then multiply by the constant. So I can do what I want to do with these things. Okay, so now here comes the part where we think a little bit. Okay. So, I need you guys to tell me what this theorem should say. I'm going to start with a sequence. Of course, I start with a sequence. Since this is the day we talk about series, then I'm going to be very interested in the sum sequence. So let's say if the sum sequence converges. Okay, so the series exists, right? The infinite series converges. Okay, if the sum sequence converges, then what can I say about my original sequence? So Leith guesses that it also converges. This is true. but it's not enough. You can say more. Well, let me ask you, if this thing converges, is that enough to say that AN plus converges? Colin. Does it have to converge to 0? Good question. Does it have to converge to 0? Well, let's see. If this doesn't converge to 0, but it converges at all, right, then it's converging to some number, which means that at the tail end of this sum sequence, you're just adding that same number over and over and over again. Now, what happens if you keep adding the same number, which is not 0, over and over and over to something? It goes to infinity. So what should that converge to? If you're, remember, this says you're going to keep adding, right? Whatever the nth term is, you're going to keep adding, right? More and more. So if this converges to something not 0, you're going to be adding something which is not 0 over and over and over again. So it better converge to 0. If it doesn't converge to 0, how could this possibly converge? No? So that's what it's going to be. Now there's more to it. What if this didn't converge? Could this thing converge? Could it be that this thing is nasty, but somehow it's nasty in some really nice way, that this thing still converges? For instance, we know we have this really nasty sequence that goes 1, minus 1, 1, minus 1, 1, minus 1. Right? But the sums there, I mean, those keep coming back to 0, right? You think, oh, that's not bad, right? Converges to 0. Why is that not right, though? So we already said that sequence, I mean, even when you start adding that up, that's kind of weird because it stays close, right? That's the key, right? If this thing starts diverging, okay, the only hope, of course, if it's diverging to infinity, of course, there's no hope that this thing will ever converge, right? Because then you'd be adding infinitely large things. Okay, this is bad. The only hope is that it's one of those ones that jumps back and forth, positive, negative, right? But then it's going to be jumping around between two values, right? 1, 0, 1, 0, 1, 0, 1, 0. It may get close to what you want it to converge to, but it's not going to stay close. Right? That's the point. Okay. So another way to state this theorem, there's nothing new. This is actually equivalent to this. If AN converges to L not equal to 0, or AN diverges, then the sum sequence diverges. Right? Or, if you like, the sum AN n equals 1 to infinity diverges. Okay, so you can write it either way. So if you know the sum sequence converges, then the original sequence must converge to 0. So if the original sequence doesn't converge to 0, or it even worse, it diverges, then your sum sequence, and consequently your series, diverges. Okay, so this is already quite nice. Okay, this requires a proof, by the way. Lath says skip it. Okay, so we'll skip it for now. Maybe I'll make it a homework problem. Yeah? Yes. Yes. In fact, remember we have this theorem which says if the absolute value of the sequence converges to 0, then your sequence converges to 0. So if it's jumping back and forth between positive and negative, but they're getting closer to 0, then the absolute value must be getting closer to 0. And so the whole sequence is getting closer to 0. Yeah. So it can jump back and forth as long as it's converging to 0. But it can't jump back and forth between plus and minus 100. That would be bad. Okay, so let me check the time. Okay, let's look at one last thing for today. So the converse of a statement. Has everybody heard this word before? The converse? Sneakers. Yes, just like the sneakers. Okay, you actually should have. We talked about this on our Fridays. So the converse of a statement, if you have an if-then statement, right? If P, then Q. The converse says if Q, then P. Okay? Now these are not equivalent. Right? You know, if you eat your dessert, or if you eat your vegetables, I will give you your dessert. This is not the same thing as if you eat your dessert, then you ate your ate your vegetables. Okay, these are different statements. Okay? So what's the converse of this? Well, the statement says if the sum sequence converges, then the original sequence converges to 0. The converse would be if the original sequence converges to 0, then your sum sequence converges. Okay? So if your sequence is converging to 0, then the series should exist and converge. That's what the converse would say. Do we think that's true? Right? If you can get really, really, really small, then you're adding small things, and so the whole sum should converge, right? That's intuitively clear. So let's look at an example. Okay, let's look at 1 plus a half plus a third plus a fourth plus a fifth plus so on. Okay. The underlying sequence is 1, a half, a third, a fourth, a fifth, a sixth. So if I an should equal 1 over n. Okay. N equals 1 to infinity. Okay. So does an converge? Does this sequence converge? 1, a half, a third, a fourth, a fifth, a sixth. Does it get close to some number? What's it getting close to? 0. Does it get arbitrarily close? Sure. Does it stay close? Sure. This thing converges to 0. Okay, so we have the hypotheses of our converse statement. Now we want to check if the conclusion holds, namely that this sum converges. Okay, and I claim that it won't. Okay, this is really weird. Okay. In fact, this is going to grow infinitely big very slowly. Very, very slowly. Okay, and let me show you, though, how you can do it. So A1, that's just 1 over 1 is 1. Okay, fine. Nothing interesting there. A2, okay, well, actually, I don't just want the sequence, but let me look at the pluses, right, the sum sequence. So A2 is going to be 1 plus a half. Okay, nothing so interesting yet. Let's skip a term and go to A4. So A4, or rather A4 plus. So A4 plus is 1 plus a half plus a third plus a fourth. And let me pay special attention to these last two terms. So a fourth is a fourth. Now a third, is that bigger or less than a fourth? Bigger. So if I replace it by a fourth, then my number is going to get smaller. Okay? So let me replace it by a fourth. Okay, so when I do that, right, I get a half. Of course, fourth and a fourth is a half. And it's now a smaller number, right, than my A4 plus. So I have 1 plus a half plus a half. So 1 plus 2 halves. Okay. Let's, oops. I'm still used to, if I get to the end of this board, going to that side. keep going. Let's look at A8 plus. Skip a lot of terms here. Now A8 plus is 1 plus a half plus, right, a third plus a fourth plus, okay, now I'm not going to write all the terms. There's a fifth, a sixth, a seventh, and an eighth. So let me just write plus dot 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 an eighth. So there's 4 terms up there, a fifth, a sixth, a seventh, and an eighth. And I know, okay, I can write 1 plus a half. And I know I can already, with this middle term, all right, I can replace that with 2 halves. Okay, that's what I did over here. And if I do that, then I'm making my number bigger. Or my number smaller, rather. Okay, so that became 2 halves. And now here, what if instead of having a fifth, a sixth, a seventh, and an eighth, I just put down an eighth, an eighth, an eighth, and an eighth? I'd be getting smaller, right? There'd be 4 eighths, so it'd be another half. This is plus, oh, wait. This one was that was a half. I'm writing this poorly. That's 1 half. Okay. So now I have 1 plus a half, and a half. Okay, that's, I mean, these aren't the halves, but down here, right? It's bigger than that. So there's 1 plus 3 halves. Okay. Now let's go to A16 plus. If I do that, I get 1 plus a half plus a third plus a fourth plus a fifth up to an eighth plus, okay, and now I have a ninth up to a 16th. So this term here, right, is greater than a half. And this term we just saw was greater than a half. And this term, well, now you have 8 things, the 9th, the 10th, the 11th, the 12th, the 13th, the 14th, the 15th, and the 16th. And if I replace them all by 1/16, it would get smaller. There'd be 8 of those 1/16ths. So that's a half. So this is bigger than a half. So again, this number is going to be greater than 1 plus 1, 2, 3, 4 halves. So do you see the trick here? Right. If I keep going like this, if I do, say, A2 to the n plus, this is always going to be greater than 1 plus, well, let's see, 16, that was 2 to the 4th, and I got a 4 here, right? 8 was 2 cubed, I got a 3 there. It's going to be 2 to the n over 2. Okay, or if you like, 1 plus, wait a second. Oh, it's not 2 to the n, it's just n. There we go. 1 plus n over 2. So what happens as n goes to infinity, this thing is always bigger than 1 plus n over 2. And what happens to n over 2? Goes to infinity. Right? So this goes to infinity. So this sum is not going to converge. Right? Because it's getting always bigger than something which is getting infinitely big. So this, by the way, this series here, this is called the harmonic series. And it diverges. And this was quite a shock, actually. If you start adding these things up by hand, right, or on a calculator, it actually looks like this thing isn't growing very fast because it isn't. And you might think it's going to converge. But this argument shows that it doesn't, which is surprising. So this theorem has to only be read left to right. You can't read it right to left. So it's not good enough just to show that your sequence converges to 0 to show that the series converges. You really need something more. Okay, so next time we're going to start on something called improper integrals. That was this last part we didn't get to today, which is going to be a way to, right, when you, I mean, I just said you need something more, right, to get that your series converges. And one of the ways that we're going to do it is to by looking at integrals whose, instead of going from a to b, are going to be going from things like a to infinity. So it's going to be a way of attacking sequences in series, but using the calculus tools that we already have. Okay,